Hi everyone, my name is Sven Otto. I'm postdoc at the University of Bonn and I present a joint work with Nazari Salih from Madrid. We look at a factor model for functional time series. And we are in particular interested in the identification of such a model and also the estimation and prediction within our model framework. This is our model. On the left-hand side, you see the functional time series YT. We have capital T functions, we have curve observations, and on the right-hand side, basically everything is unknown. We have some intercept function, we have a common component and an idiosyncratic component. And the common component consists of factors and loading functions, and we have capital K factors. And the factors are dynamic. They follow some stationary time series model, in our case, a VRP model, whereas the errors are uncorrelated. And to motivate this model, let's have a look at a popular model from financial econometrics, the Nelson Siegel model for bond yields or yield curves. So a yield curve is this here, where you see on the x-axis the time to maturity of, for instance, a US government bond here. And on the y-axis, you see the yield with respect to this maturity. So the interest rate when you buy such a bond. And this is monthly data. So for every month, you get such a curve. And you might want to model the dynamics of this curve to get, for instance, forecasts. And the Nelson Siegel model is actually nested within our model, but assumes to have predefined loading functions. So we have 3 loading functions. K is set to 3, the psi's are fixed, and then the model is very easy to estimated, to be estimated. So we can just estimate the factors by least squares and then estimate also the dynamics by least squares and get a really easy to apply forecasted yield curve. It works quite well in practice, but of course we have the limitation that these loadings are not necessarily optimal. And we would like to have predefined loading functions. Instead, we would like to impose identification conditions for our dynamic functional factor model. And for this, we need to introduce some notation. We work in the Hilbert space, in the L2 space. And if we have enough moments, then we have a covariance function, and we can extract eigenvalues and corresponding eigenfunctions from the corresponding covariance operator. So we have 2 sets of assumptions. Assumption 1 is on the common component and assumption 2 on the idiosyncratic component. Assumption A and B are for separately identifying the psi's and the f's. So the psi's are orthonormal and the f's are contemporaneously uncorrelated and have some ordered variances here. Assumption C is very important to separately identify the common component from the idiosyncratic component, because it simply says that the kth factor is correlated, autocorrelated, either with itself or with any of the other factors, which is in contrast to the property of the idiosyncratic component, which is a martingale difference sequence. So this is uncorrelated. This is the fundamental difference in the dynamic structure, which helps us to identify the split, so the number of factors here, k. D simply states that we have a causal process, F is a causal process, and E is just a regularity condition for estimation of the factor dynamics. We already talked about A. B, we need some weak orthogonality between the errors and the loadings, and also the errors have to be limited in terms of variance compared to the factors. In D, we allow for some cross-correlation of the factors and the errors, but only in a weak sense, so that asymptotically it does not play a role. This is our identification result. First, the expectation of our y curve yt is equal to the intercept function. Then we have this global covariance kernel here. Yt might be non-stationary or locally non-stationary at some points, but due to this assumption here, but on average, this non-stationarity drops out. So we have a global covariance kernel C here. Which consists of the covariance kernel of the common component and the error component. And from this covariance kernel, we can extract the eigenvalues, which turn out to be the variances of the factors, and corresponding orthonormal eigenfunctions, which turn out to be the loading functions. And then the factors are just projection coefficients. Loadings and factors are only separated up to sign change, but their product is identified. So also K is now identified because K is just the largest index of these projection coefficients, which are ordered descendingly. So the eigenvalues are ordered descendingly. The largest index for which we have some autocorrelation. So now we have identified our model, and we can use this result to get a moment estimator. So we can simply replace the population by the sample moments and use the sample mean and the sample covariance function. We can extract eigenvalues corresponding orthonormal eigenfunctions, which are the empirical functional principal components, and the factors are the corresponding scores. These are then the empirical functional principal component scores. So we can use this to get a fitted curve. In the second step, we can estimate K and P by a suitable information criterion. I will introduce that in a minute. And then we can also get predicted curves for the number, for the estimate using the estimated number of factors. Yeah, these primitives, so these sample counterparts are consistent for the population counterparts in the square root T sense. And maybe to introduce our estimator for K and P, let's look at the forecast error curve. When for the forecast, for the one step ahead forecast, we use L factors and M lags instead of the unknown K and P. And the idea is just to select L and M so that this forecast error curve is minimal on average. To be more precise, we look at the mean squared error of these forecast errors. And and our criterion has this form. We look at the logarithm, and we need some additional penalty term, which is actually necessary for our information criterion to be consistent. It's similar to the BIC type, to the BIC criterion, where we also need a similar type of penalty term to get a consistent estimator. I will skip the prediction bands. We also have simulation results where we see that our estimator actually is in this setting also here has very good mean squared error properties, whereas the conventional estimator from Auer and al. And others has some difficulties here. And the reason is that it does not have this penalty term and is actually not consistent, at least within our functional factor model framework. We also have an application. I will skip that. And essentially, we can show that we can also beat the Nelson Siegel model in terms of forecast performance on average. We also have some prediction bands. Yeah, to sum up, we have introduced a framework for a functional factor model. And we have identified this model, and we have a consistent estimator for this model, which is easy to apply, which is based on functional principal components. And we've introduced also an easy to apply information criterion to select the number of factors and lags in a consistent way. So I guess time's up. That's it. If you are interested, the working paper and R package are coming soon. You can also write me an email. So thanks for watching this video, and goodbye.